everyone. Today I will be talking about the assistive devices that we are working with to help people with lower limb amputation. As many of you know, limb amputation leads to all sorts of gait impairments, one of which is higher metabolic cost. This increase in energy cost is potentially due to the fact that conventional prosthetic devices are all passive. And so some active devices have tried to mitigate this issue, like the biome shown here, for example, but the improvements in energy costs are minimal, and so not quite as much as we would like. On top of that, a study a few years ago showed that increasing prosthesis ankle work doesn't seem to have a strong effect on metabolic cost. And so we're wondering, why could that be? And we thought that maybe it's because a lot of these devices are hand-tuned and not exactly optimized to the individual. And so we decided to try optimizing systematically device prosthesis control to see if this would assist performance. And so we have a prosthesis emulator over here. It's a prosthesis that is tethered to powerful off-board motors to a computer. It allows us to very quickly change the control profiles of the device. The device itself is shown on the right. Vince will talk about it in more detail tomorrow. But the point here is that it's very lightweight and allows us to dictate all sorts of behaviors to it that we can test and see how people respond. And so we wanted to optimize this performance, and we optimize it using a system that we call human-in-the-loop optimization. Basically what happens is we start with a generation of control laws. So control laws with a certain mean and distribution of controller parameters. Then each control law is dictated to the individual, and they get to experience it for about 2 minutes while we measure their performance, in this case metabolic cost. And then, after all of the control laws are evaluated like this, a covariance matrix determines the next generation, the next set of control laws, and the cycle repeats, with the idea that eventually the control laws, the parameters of the controller will just kind of come to the ideal for that particular user. We used this system before, this optimization strategy, and it worked well with exoskeleton assistance. So this is from a study a couple of years ago where exoskeleton assistance for unimpaired individuals was optimized, and on average users reduced energy expenditure by about 24%. So this approach works. But when we applied it to the prosthesis, we saw no improvements in energy cost. And so we thought, okay, well, we have a different system, we have a different user group, maybe there are certain things about this approach that we need to modify. So we tried a lot of things. We tried increasing the number of control laws. We tried increasing the number of generations we let the system optimize for. We tried changing the controller architecture that we optimized, or letting people experience each controller for longer durations, but still none of those really affected energy cost. We couldn't really optimize. And so we thought, well, why is it that people with amputation can't take, or don't seem to be able to take advantage of this assistance? And it's potentially because on a joint level, they need to sense, we need to sense what's happening at the joint level or directly control what's happening at the joint in order to take advantage of assistance. It's also possible that these adaptations are on a body level. So maybe amputation leads to changes in the learning strategy of how a person takes advantage of assistance, or it constrains balance or coordination in some way. It could also be external. So maybe people just need longer training durations or different control architectures. External factors are difficult to isolate and say definitively that that's not what it is, but we've worked a lot with, we've changed a lot of things, and we've tried a lot of things modifying externally, and so we're not really going to focus on that today. Instead, what I want to focus on is this sensing. What if people could sense what's happening at the joint? And so we tested this with individuals with amputation by putting an exoskeleton on their sound side to see if, in this case, they could take advantage of the assistance. It looks something like this. And the particular assistance profile that we modified is from the previous study I talked earlier where unimpaired individuals reduced energy cost by 24%. It's basically just a torque profile that's defined by 4 different parameters. And I have some preliminary results. So over here, these are our participants with amputation. And over here I'm showing the generation number. Each generation has about 8 control laws that people are trying, so it's about 20 minutes long. And the conditions are 0 torque, when the device is on the individual but not providing any assistance. There's optimized, so after a certain number of generations, how the optimized parameters performed. And then there's just normal shoes for comparison. And as you can see, the reductions aren't that great. Now these two participants 2 and 3, haven't quite completed the study yet. That's really funny. But still, the reductions are limited. They're smaller than we would expect. And just to remind you, this is what unimpaired individuals showed. That 24% reduction after just 4 generations. So we are going almost 5 times as long and not seeing the reductions as large as that. And so, going back to this slide, it seems that something is happening. We can provide, in some cases, some assistance, but it's probably not fully explained by just sensing at the joint. It's probably something else is going on. Direct control is an interesting thing. I'm going to shout out to everybody to go see Carol Wilco's poster on Wednesday, right? She's going to be talking about directly controlling the device. Yeah, so that's it. Thank you.